So thank you, Kirsten, for this kind invitation to be here today. So Kirsten was my colleague in New York, and although many of us were sad to see her leave, I do admire her interest and enthusiasm to contribute to this very exciting Middle Eastern American joint venture, especially amidst the wave of isolationism that has been spreading through the US since January 2017. So it's a pleasure to be here. It's a pleasure to visit this beautiful campus. I've been willing to visit for a long time as NYUAD Abu Dhabi bridges the Arabic world where I grew up and New York City where I built my scientific independence. And today I would like to tell you the tale of the best medicine of all, which is our own immune system. Are you hearing me? I think there is an echo here, no? Is there an echo? Should I do this? Is it okay? So I'm going to start the story with the beginning of it, which is in the late 1800s. So in the late 1800s, the thought was that the outcome of a microbial infection was mostly due to the microbe. If a microbe was too dangerous, the patients will die. If the microbe was mild, the patients will survive. And Elie Mechnikov, this phenomenal Ukrainian scientist, was going to prove this theory wrong. So what Elie Mechnikov did, he was then a zoologist. In a now landmark experiment, he introduced the thorn of a rose into a transparent starfish larvae. He was a zoologist. And then he observed what happened when he introduced the thorn. And what he saw many cells crawling and trying to attack the thorn. And he called that phagocyte. He called the cells phagocyte. The phagocyte for the Greek word phago, which means to devour, to eat, and cyte for cells. And he described two types of phagocyte. Big phagocyte, which he called macrophage, which are cells that I've been studying for 2 decades now. This is not really working. Do I have a pointer here? The pointer should be this. Can I have a pointer, you think? And then a smaller phagocyte, which he called macrophage and now are called neutrophils. And he showed that these macrophages were also present in rodents and they were present in humans. And he stopped being, in fact, a zoologist and became a biologist. This is not... I have to press very strongly, like a man. Well, you sure? Let's forget about it. Just follow me. I'm going to use my arrow here. And then so he described this group of cells. But in fact, what he described is a cellular system that was here, that was present to defend us against the external environment. And then he showed that this process of eating, of phagocytosis, was in fact a process that helped host defense against foreign attack, host defense against microbe, but also a process to eliminate potentially damaged cells in tissue, for example, that turn over quite rapidly, for example, keratinocyte in the skin or epithelial cells in the gut. So what he described is a cellular system that protects us against damages. And for this discovery, he received the Nobel Prize of Physiology in 1908, which marks really the birth of immunology as an independent scientific discipline. So now we know that the immune system contributed to the survival of the human race, and it is believed that the once very powerful Mayan Empire may have abruptly disappeared in the 9th century due to a widespread disease, potentially parasitic diseases, to which the Mayans were not immune against. And we know also that another widespread infection, now caused by a virus called the influenza virus or flu, caused more than 50 million deaths, more than World War I, suggesting that indeed immunity against something or the ability to fight an infection was critical for our survival. And now we have the proof, the genetic proof, that indeed the immune system is required for us to survive. So we have detected several gene defects that in fact altered different branches of the immune system that I'm going to introduce in a minute. So here is a kid that is affected by one of these very severe genetic defects that completely abrogate his immune system, and this poor kid is unable to live outside. He has to live in a bubble. We call that the bubble boy. Now these kids are being treated with bone marrow transplant, but this kid, if without the bone marrow transplant, he will not be able to survive any type of very harmless little microbe. We know also that a virus that attack your immune system, for example, the human immunodeficiency virus, can also lead to lethal infection, can also lead to cancer, and can be fatal. Again, proving the importance of this immune system. So now, many decades later, we know that the immune system has four main tasks, and these tasks are in fact being carried away by two branches of the immune system, which I'm going to try to introduce to you quite simply today. There is this innate branch that needs to recognize a threat. We need to be able to recognize what's harmful, and this is a very important step because we cannot react against things that are against normal tissue, against normal cells. So this ability to recognize is regulated by a big array of receptors that is expressed by this macrophage that I just discussed about, or their cousin, dendritic cell, that were in fact discovered in the 1970s, a discovery for which also the scientists who discovered them received the Nobel Prize in 2011. So this recognition is very important. Now, once the threat is recognized, the threat needs to be removed. And it is removed by immune effector function. There is two types of cells that are going to try to attack, to eliminate, for example, the flu virus. And this is being carried away by the innate cells. Macrophage can eat and destroy. Neutrophil can eat and destroy, but also an adaptive immune system. That is going to be educated by the innate cells, educated to recognize and kill. And it's a very sophisticated group of cells that I'm not going to detail, but I'm just going to show you the complexity of this cellular organization. And then there is a very important step, which we are still trying to really understand today, which is regulation. When this immune response, any type of immune response, needs to be regulated, otherwise we will be dying of excess of inflammation. Each type of infection, when you have a little skin infection, if it's not regulated, then you'll be submerged by inflammatory molecule that can in fact be fatal. So we know now that regulation is a key step of an immune response. And then finally, the immune system can remember the threat. And this is the basis of vaccination. It remembers so that it can, in fact, induces a faster and stronger response against subsequent challenge. So all these tasks are, in fact, the subjects of many investigations throughout the world by immunologists and others. So now I'm going to describe to you, quite simply, I hope, the critical steps that lead to the initiation of an immune response against a bacterial infection. So I see a little boy here. So try to tell me later whether you understand what I'm going to use very simple cartoons. And I tell my first year students, if you remember these 4 slides, then I declare you an immunologist. It's quite simple and it makes a lot of sense. So here we have a bacteria in the lung, a tissue, and it can be a bacteria in the skin. Remember when you had a little infection somewhere, right? Try to imagine, your skin being a little bit red. So there is an infection that occurred. There is a little bug, let's say a bacteria. So this bacteria is going to be sensed by this macrophage that I described. The macrophage arrive and realize that there is something that's not normal because they have the right receptor to recognize it, even if they've never seen it before, which is very different from the adaptive system that needs to be educated. Now, macrophages that need to be educated, they are present in every single tissue. Every single tissue, the brain, the liver, the muscle, the kidney, all your organs have this group of cells that Mechnikov, in fact, described. And they are going to try to see whether something is wrong. They constantly survey for a threat. As soon as they see a threat, in this case, the bacteria, they are going to react to it. And they react to it by producing. Okay, so the bacteria arrive, sense this is a dendritic cell. In fact, where is the macrophage? The macrophage is here. It will be so great to have a pointer that works, but I'm going to use this. So this is a macrophage with the bacteria. This is a dendritic cells with the bacteria, okay? So they sense, and what they do, they release cytokine molecules. It's quite extraordinary. And these molecules are going to bring cells from the blood, for example, neutrophils, that are going to come and accumulate. Okay, there's a lot of molecules. And there is these neutrophil, white blood cells that come, and they are going to devour the bacteria and try to eliminate it. But at the same time, what's going to happen is that you have to we want to remember this type of threat. So the dendritic cells, the cousin of macrophage, are going to take this bacteria, migrate to the lymph node. You know these things that are swollen when you have an infection, they migrate there. Every organ is drained by a lymph node. It goes to the lymph node, and then it's going to educate your adaptive immune system. And in educate cells, it's going to tell very strong effector lymphocytes that have a very serious killing machinery. It's going to educate them against this threat. And this regulation is studied by many groups all over the world, which is a very complex process. The dendritic cells arrive here in the lymph node, and they are going to tell lymphocyte, okay, go back to the site of injury and help us eliminate the threat. And this happens all the time. So these T cells, the green cells, start to multiply. There is a group of lymphocytes called the B cells produce antibodies. And these antibodies and the T cells go back to the site of infection. They arrive, and then finish the job. And they clear, the injury. And while they clear it, they will always remember it. Now, if you have a subsequent challenge, the T cells arrive very fast. Here it takes approximately 6 days for the T cells to arrive. Here they can arrive as soon as 1 day after the infection, and you have a much stronger response. So the understanding of this process made scientists realize that, in fact, the immune system can be harnessed to protect against microbes. Now, we understand that there is a system that protects us. Can we now use it to protect us better, right? And here, I'm going to these 2 scientists that are responsible for significantly prolonging human longevity through the development of microbial vaccine. So here, on the right is Edward Jenner, who is the father of vaccine. So Edward Jenner is a British scientist who, in fact, realized that milkmaid, so people who works with cow, were protected against smallpox virus. At that time, in the 1800s, 10 to 20% of the populations were dying of smallpox. Terrible disease. And there was this tale that milkmaid were protected, but this milkmaid also developed a disease called cowpox disease, which was due to a virus that resembled the smallpox, but was affecting mostly the cattle. So what he did, he took the pus from this cowpox blister that he found on a milkmaid called Sarah James. He took it, and then he injected it in the arm of the son of his gardener. Well, that's brave. But he did something even braver. What he did then, he then injected the son of his gardener. It would have been better if it was his son or himself, but well. And he inoculated this poor little boy with the smallpox. And the patient didn't develop the smallpox. And this process is called violation or vaccination. And really established that by exposing, in fact, the patients by a virus that resembles it, you can maybe be protected against the real virus, against a large challenge of viruses. But what he started to do is also inject the real human virus to patients. And in fact, in 1853, after his death, there was mandatory vaccination in England, and in 1979, smallpox was eradicated thanks to his really demonstration of the benefit of inoculation. And then next to him is Louis Pasteur, who coined the term vaccine in honor of Edward Jenner, and he now used this term to describe other protective inoculation and extended vaccination to rabies, for example, and anthrax. And now there are several mandatory vaccinations that help protect us against many different types of diseases. Okay, so the vaccine success really made scientists realize that the immune system had this fantastic killing machinery, but also had this phenomenal memory, right, that you could use to, in fact, first detect an abnormal cells, kill it, and remember to kill it if it comes back. And here the work of another extraordinary physician was going to start another medical revolution. Here, I'm going to talk about the work of William Coley. William Coley was a surgeon, a cancer surgeon in New York, in an institution now called Memorial Sloan Kettering, which really is dedicated to cancer. And William Coley was a surgeon and really focusing on soft tissue cancer called sarcoma. And devastated by the death of his first patient, he started to read the literature for treatment that could have saved his patient. He was a surgeon, so at that time, cancer was treated only with surgery. That's it. And what he discovered is that other patients with the same type of cancer had their cancer mysteriously disappear after a bacterial infection. So what he decided to do, he purposefully, again, it's another brave surgeon, but here he was injecting the patient, so well, he really wanted to save him. He injected the patient's lesion with a bacteria, a very severe bacteria called Streptococcus pyogenes. And what he found is that the patient had a dramatic recovery. And then he started to inject many of his patients, and in fact, he had some phenomenal responses, and some of his patients remained cancer-free for many years. However, the results were inconsistent, and ultimately immunotherapy was abandoned for more controlled therapies such as chemotherapy and radiation. But this idea of building an immune response against cancer cells was really somehow established and really led to the development of this field of cancer immunology. And now we all know, so I'm a cancer immunologist by training, that if you look at a tumor lesion, in fact, the majority of the cells are not these oncogen-driven cancer cells, but are immune cells. Any cancer lesions have a large number of immune cells in the lesions. So lesions is not homogeneous at all. You always see a large number of macrophages and a large number of T cells. In fact, it's incredible when you look at it, it looks like a granuloma against TB. The tumor is in the middle here, and then you have immune cells all around it. We know also that tumor cells express many abnormal proteins due to somatic mutation, and this protein could be recognized as abnormal by the immune system. And in fact, we also know that these dendritic cells, the cousin of macrophages, were described in 2011, remember, Nobel Prize of Physiology recently, constantly capture tumor cells and present it to T cells. The same way we present bacterial infection to T cells, so branch of innate system, we build, they migrate to the lymph node, they present it to T lymphocyte, and this is also very studied. So the T cells, we know, and we've detected T cells that can recognize, there are two types of T cells, you don't have to remember that can recognize a specific tumor antigen because tumor cells, in fact, express very unique feature on the cell surface. Yet, these lymphocytes are not killing the tumor. And this was a puzzle for many cancer immunologists for many, many years. And the answer to this question led, in fact, Jim Allison to discover a regulatory molecule that was dampening the T-cell response against cancer. And this is leading to what's called the immuno-oncology revolution, transforming cancer care currently. So what Jim Allison discovered is this molecule, CTLA-4, which was already cloned by other scientists. In fact, a French group led by Pierre Goldstein had cloned it in 1987 and showed that it was expressed on activated T cells. But what Jim found is that when these dendritic cells present an antigen, let's say a bacterial antigen to T cells are these effector cells, right, that can come and kill an infected cell or a tumor cell. They also constantly regulate it because they are afraid of excess inflammation. And this regulation is driven by the induction of a signal, in this case CTLA-4. This is a molecule that's going to limit the ability of T cells to expand, the ability of T cells to kill. So what he did is he developed an antibody against CTLA-4, something to block CTLA-4, and he injected it into mice with cancer. And what he observed is that when he blocked CTLA-4, in fact, the tumor disappeared in these mice. This is tumor growth, and this is a mouse treated with anti-CTLA-4 antibody. You can see the tumors are much smaller. So this was sufficient to really drive a clinical trial. So let's see. First, so this is what he said. So he now use this term checkpoint. Checkpoints, he described checkpoints as immunoregulatory molecule that can dampen T cell activity, and he suggests that tumor cells evade the immune system by increasing immunoregulation. And this led to this now landmark clinical trial in metastatic melanoma patients that don't respond to anything. And you may think that these, in fact, responses are not so great, but I'm going to get through to lead you through it. So this is melanoma patients, metastatic melanoma patients, evaded everything. They're being treated with a placebo, let's say, or a vaccine, or the CTLA-4 blockade. And what we observed is that when the patients were treated only with a molecule that were increasing T cell activity, we didn't do anything against the tumor cells. Some patients responded, but among those that responded, they responded forever. And in fact, now 7 years later, some patients are cancer-free. Okay, and that led to the FDA approval of the checkpoint blockade for the treatment of metastatic melanoma patients. This is a big year for cancer immunologists, because after that, so the problem with CTLA-4 is that it's a toxic molecule, because in fact it regulates what's called the T regulatory cells, and you have to have these cells quite active in the gut tissue, otherwise you have a lot of inflammation. So patients develop very severe colitis, and in some cases it was prohibitive. But what happened at the same time is that we started to think about checkpoint molecule, and another checkpoint molecule was in fact rediscovered, was cloned before, and its ability to dampen anti-tumor immunity was rediscovered by several groups at the same time. And this molecule is called PD-1. Remember PD-1 because you are going to hear about it for many, many years to come. So PD-1 is another molecule that is expressed on activated T cells, again induced by now antigen-presenting cells, dendritic cells, or macrophage. Each time a T cell is activated against, let's say, tumor cells, this molecule comes along, again to dampen its activity. Okay, so if this is engaged, if PD-1 is engaged, T cells cannot kill. If now we block it, T cells start to kill. And I'm going to show you how they kill, because this is quite beautiful. I hope this is going to work. Okay, so here, tumors are green, and the T cells are gray. Look at the T cell is going to eat the tumor cells. This is being filmed in vivo in mice. Disappear. We call it the assassin. They go, they eat, and they eat very efficiently. Now, there is a cell there. There's also a tumor cell that's not being eaten. So what we did here, we transformed the tumor cells. We made tumors that didn't express a checkpoint molecule and express a checkpoint that can engage it on T cells. Now we know that in some cases, these cells can still evade and one can be killed, right? So we are learning about how to make these tumor cells more sensitive against an immune response. But realizing this killing ability is extremely important, because now we are going to use natural system to really attack damaged cells, and the cancer is going to be treated as the cancer cells. Now realize that the T cells is going to attack only the cell that it needs to be attacked. The rest is going to remain intact. It never happened with chemotherapy. Chemotherapy often lead or always lead to the killing of mostly proliferative cells. Radiotherapy will irradiate all the cells that are surrounding the tumor. Now, targeted therapy are these drugs that target the dysregulated pathway in the cancer cell. The problem with the cancer cell is it's a highly dysregulated cell. So each time you try to target the molecular pathway, they know how to evade. This is why they became the cancer cells. So we believe that by really attacking the environment that is not so dysregulated, it's not an abnormal compartment, it is modulated by the tumor compartment, we may gain in terms of tumor outcome. In any case, this led to a frenzy. In fact, in the investment world and in industry, there has been a race to generate, in fact, antibody against checkpoint blockade. Merck was racing with BMS. BMS is the first industry that made this anti-CTLA-4, had these beautiful results in melanoma patients, but Merck was trying to make an antibody against PD-1. Both of them now starting to make PD-1. Other industry jumped in the field. There was many biotech that started to think about investing in immuno-oncology. And then we had these beautiful results, and incredible results that that really it's impossible to resist. So here, Merck did this clinical trial where they compared in metastatic lung cancer patients, an anti-PD-1 antibody. Patients were treated with one agent, an antibody against PD-1, this molecule that makes T cells more active, and compared it to chemotherapy. And they observed dramatic response in favor of anti-PD-1 treatment, especially on those where tumor, in fact, express the ligand of this checkpoint molecule. I won't go into the detail, but this translated into increased overall survival. So lung cancer, metastatic lung cancer, is a really devastating disease that really resists traditional treatment, including chemotherapy and radiation, respond to some targeted therapy. This was a dramatic result. And this really led to this paradigm shift where historically we will target the tumor cells, and now what we are doing is targeting the environment. But really what we want to do is to combine these two types of treatment. We should target the tumor cell, but also target the environment, and the environment can be used to really eliminate it. And other groups are trying to target the endothelial cells that provide blood flow and oxygen to the tumor. But what I want to emphasize is that cancer regimen is always going to be a or combination treatment. But the discovery that monotherapy agents that are only driven to attack, to strengthen an immune response is leading to dramatic responses suggests that we can do better in many types of cancer. So now the FDA-approved cancer indication for checkpoint blockade are dramatically increasing. PDN approval for PDN blockades have been given in many cancer types. CTLA-4 is treating mostly melanoma patients because it's too toxic. The toxicity of PD-1 is much more manageable. The number of immuno-oncology companies are significantly expanding, and major industry are now investing quite significantly in immuno-oncology. So it's really a revolution, both in the investing world and in the scientific world. However, responses to immunotherapy remain limited to some patients, and in some cancer patients, for example, in pancreatic cancer, we are not observing very significant results. And now, understanding why some patients respond and some do not respond to immunotherapy, we believe can lead to novel immuno-oncologic drugs. And we believe also that we should also be stratifying patients according to this regulated molecular pathway to really increase tumor response to treatment. And it's what we call precise therapy. So in general, in all human diseases, we make a diagnosis using CL, a microscope, right? And we lump diseases together. So we will say, well, you have a liver cancer, it's adenocarcinoma, so we know the cell type of cancer that is generating this liver cancer, but we rarely treat based on the molecular pathway, although cancer is more advanced than most diseases where targeted therapy, where we try to really target the molecular pathway is being introduced, but generally, in disease other than cancer, we try to lump it. So, for example, atherosclerosis, we will all have the same treatment, yet we believe that there is, in fact, probably a lot of heterogeneity in a group of disease that are labeled, in fact, histologically. So what we started to do in my lab is try to really define at the cellular and molecular level the immune compartment of cancer. We have a strong focus on lung cancer and more recently on liver cancer. And what we are doing is taking every single cell that are present in the tumor lesions and analyzing all the gene and gene transcript and molecule to learn about all the dysregulation that occur in this immune compartment. And then hoping to discover novel checkpoint molecules that are really regulating an immune response, but also better stratifying patients so that patients that have an increased PD-1 expression on T cells will receive PD-1 therapy. Those that don't maybe should not receive PD-1 treatment. So this is an example of a recent result that we obtained and that we are very excited about. So what we found in a group of cancer patients, we found that macrophages, those macrophages that Meshnikov discovered, were acting in a very dysregulated manner, and they're producing very immunosuppressive molecule. So And we were very intrigued by the expression of a molecule, let's say, on this macrophage. So what we do now, we went back to an animal model, we developed a lung cancer model, and now we remove this molecule from macrophages. And what we observe is that when we remove this molecule from this group of macrophages, the tumor growth was strongly reduced. So the next step will be to now go back to patients and say, first, can we modulate? How can we modulate this molecule? Can we use an antibody to modulate it? Can we rescue an immune response when we do that? And potentially do a clinical trial. So this ability to now go and really analyze the tissue lesion at the cellular and molecular level can be really dramatically, in fact, enhance our understanding of tumor immunity, but also lead to the discovery of new therapy. Is there a time somewhere? 30 minutes. Okay. So now moving beyond cancer. So what I showed you in cancer is that there was too much immunoregulation. And if we now make the T cells or make the immune system more active, we can gain in terms of tumor response, right? Please remember the difference between immunotherapy and chemotherapy in lung cancer, right? We really improved the number of patients that responded, and we improved overall survival in patients. But there are diseases where there is an excess immune response. And excess immune response can be detrimental. So remember, human probably that survived today was those that have a strong immunity to microbes. Otherwise, we would have died with the Mayan, right? So probably we inherited somatic or genetic mutations that affect our response to environmental trigger. And it is possible that, in fact, we have quite a strong immune system. And in fact, we have now discovered many susceptibility genes that are associated with inflammatory disease, such as rheumatoid arthritis. I don't know whether you've heard of this disease, but this is a very debilitating disease in which patients spontaneously develop an inflammation of the joint, and they become completely crippled. There is also this disease called inflammatory bowel disease, where there is spontaneous excess of inflammation in the intestine, leading to chronic inflammation, chronic diarrhea, sometimes fistula, abscess, and it's a terrible disease that in fact increases in Mediterranean regions and also among Ashkenazi Jews. And there is also this disease called psoriasis, where there is excess inflammation in the skin. Now, what we realize is that all these lesions are due to an excess inflammation that are due potentially due to genetic mutation, potentially somatic mutation, and they all share this excess molecule called excess TNF. And there is additional molecule that have been found to be increased in these lesions. So a series of clinical trials attempting to block this inflammatory response have been, in fact, initiated in patients, leading to dramatic results. So patients with rheumatoid arthritis now have their life completely transformed with this drug called anti-TNF antibody blockade. We block, with an antibody, we block this inflammatory cytokine. And this has really transformed the life of these patients. Anti-TNF has also transformed the life of patients with inflammatory bowel disease. And now more recently, another antibody blockade against IL-17 has completely eliminated severe psoriasis. We don't see psoriasis or severe psoriasis in our clinic anymore. In fact, some psoriasis doctors told me that they have to refocus completely their clinics. They don't see these patients anymore. So our understanding of this immune pathway is helping us, in fact, treat very serious diseases. There's another disease that's quite frequent, in fact, in this region, which is gout or Mediterranean fever, not in the Middle East, but very frequent in North Africa. This is also being treated with the regulation of what's called inflammasome, the release of also this inflammatory cytokine. So this immune system can also be detrimental. And I'm going to highlight this a little bit further by talking about atherosclerosis. So atherosclerosis is #1 cause of death and disability in the developed world, but also in the UAE. I was told today that this is the #1 cause also here. And atherosclerosis is an inflammation of the vessel that due to excess deposition of bad lipids. And we thought that, in fact, regulating your lipid should get, in fact, strongly improve your vessel function. It turns out that, in fact, this accumulation of lipid also leads to an inflammatory response. The immune cells arrive, try to clean the lipid, and this inflammatory response is also going to be detrimental to the vessel. So there has been a recent study published also in the New England Journal of Medicine. This is the Bible. So when it's published there, usually it leads either to FDA approval or, or to a series of clinical trials that are going to come behind it. This is a very serious journal. And what this study showed is that by blocking another inflammatory cytokine, in this case IL-1, was dramatically improved cardiovascular event without affecting the lipid level at all, suggesting that, in fact, reducing your lipid may not be enough, and then you need to combine the modulation of your immune response and also modulating, in fact, the lipid accumulation in vessels. And now, if I have a few minutes, I'm going to talk about another disease, again, where immunomodulation can be very important. And the next frontier, we believe, when we are done treating cancer and we are done treating inflammatory disease, are going to remain these neurological diseases, which we still know very little about because of a lack of models and lack of also of tissue. It's very difficult to biopsy a brain, whereas we biopsy lung cancer constantly. I biopsy gut tissue all the time. I have access to psoriasis lesions, but I never have access to brain lesions, right? It's quite difficult to biopsy a brain tissue. However, we are noticing really an increased number of neurodegenerative diseases, Parkinson, but mostly Alzheimer's disease. And what's incredible about Alzheimer's disease is that all the susceptibility genes that are associated with Alzheimer's disease are genes that are expressed in these macrophages. So what we are realizing is that, in fact, an aged macrophage is unable to eliminate damaged neurons. And this defect of clearance, which, one of the key functions of these immune cells is also to get rid of debris. This inability to clear this damaged neuron is going to lead macrophage to produce some bad inflammatory molecule that is contributing to cognitive dysfunction. So there are many companies that are trying to restore the clearance capabilities to these brain macrophages called microglia, and see whether this can in fact reduce the accumulation of what's called this plaque that form in the Alzheimer's disease brain, and by modulating these immune cells, we may gain in terms of cognitive function. All right, so I hope I convinced you that there is a lot to learn about the immune system, and not to be used, in fact, to treat diseases such as cancer or neurodegenerative diseases or inflammatory diseases. And really understanding this molecular pathway will help us, in fact, devise a precise treatment to treat not the organ damage, but the molecular pathway that's defective. And then maybe, since we are talking about women in science, I thought I'll give you a very brief sense of my journey, and maybe I can it will inspire some of you, or not inspire you. But I thought I'll describe my academic journey, which started in Algeria, so an Arabic country, 4 hours away from here. A Muslim country also, where I started medicine, where I did medicine, and then I moved to France to learn about bone marrow transplantation. Bone marrow transplantation is really the first successful immunotherapy, which was used to treat these patients with immunodeficiency, but also treat heme malignancies. And then I obtained a fellowship to do a PhD after I finished my residency in hematology oncology to learn immunology more in depth. And the reason why I decided to do a PhD is because my patients, as I was in the clinic, most of them were dying of the chemotherapy I was giving them. And it's very saddening when, I loved clinic. In fact, I am from a family of physicians, and I really enjoyed very much spending time with patients. There is a direct reward when you are with the patient. It's very sad when you realize that the treatment that you are giving is probably a little bit empirical, and that probably there is a lot to be learned. And this is where I decided to focus on understanding this immune response that I was inducing in patients. So I went to Stanford, and at Stanford I spent a lot of time, 4 years, doing a PhD after having finished 15 years of medicine. And after that, I had decided to focus my scientific life to studying immunology against cancer, blood cancer, and solid tumors. And this is where I was recruited to Sinai. And so it's a long journey. It's a very long journey. It's a long journey, regardless whether you started in Algeria or you started in New York. It's always a long journey for a scientist, because building a scientific niche and scientific expertise requires first enormous amount of work, but also enormous focus, right? So there are many ways where you want to stop, because there's many reasons, many failures along the way. And it requires, I think, a lot of focus, a lot of scientific engagements, a little bit of passion, or a lot of passion, depends on the personality, but also some kind of ambition, the desire to really want to achieve something and to contribute. And really realizing that persistence matters. And now I can say that more than ever, is that science is really a marathon, but there is many ways to run it. And there is no one way. And it's very difficult, in fact, to suggest a path, because there are many paths. But if I were to start a scientific program in the UAE, what I will think about is, how can I be unique? How can I take advantage of the environment here? And as an immunologist, I will say, well, is there a specific virus-induced cancer that I can study that's really happening only in the UAE? How can I take advantage of this population? Is this population unique? Is there a lot of consanguinity I can learn from? Because there is all this genetic defect that can affect the immune response. So strategizing, thinking about what type of impact you want to have in science. And it's okay to have a small impact, but a real impact, and constantly thinking of how you can contribute, really get you closer to the goal. And I'd like to finish with this quote by Stephen Hawking, who this phenomenal astrophysicist who, in fact, died a few days ago, had this very severe motor disease, who said, one, remember to look up at the stars and not down at your feet. And two, never give up work. Work gives you meaning and purpose, and life is empty without it. And I think this is what really drove me to persist, is that it's really, what else can we do? This is my lab, a fantastic, passionate scientist, and here I list all the colleagues with whom I brainstorm constantly on the future of science. Thank you very much.